Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 1 from module 2 is Ferris wheels, tracking the height of a passenger car. Exploratory challenge, challenge 1, the height of a Ferris wheel car. So George Ferris built the first Ferris wheel in 1893 for the World's Columbian Exhibition in Chicago. It had 30 passenger cars, was 264 feet tall, and rotated once every 9 minutes when all the cars were loaded. The ride cost 50 cents. So I don't know if this is a photo of that, but I was looking at that wheel and it looks like there's more than 30 cars. So who knows? But anyway, part A says, create a sketch of the height of a passenger car on the original Ferris wheel as that car rotates around the wheel 4 times. Okay, so sketch. So the first thing you want to do is the x-axis is the number of rotations. So if I come out here and put 4 right there, go halfway, this would be 2 rotations. Split that in half, there's 1, and split that in half, and there are 3. Okay, 1 rotation, 2 rotations, 3 rotations, 4. So you get in the car at ground 0, right here. So the height of the passenger car maximum was 264 feet. Okay. So right up here, I would put 264. Scales really don't matter, but it kind of helps. This would be 132. And if I cut that in half, half of 13 is 6.5. So that'd be 66. 66 plus 66 is 132. Add 66 to 32 and it's 198. So that'd be right here. Okay, and I guess that's enough for now. So here is obviously the origin where we start. So we're getting in the car right here at 0, 0. Now it says to create a sketch. I've been happier if it said create a graph of the height of the passenger car. Anyhow, here we go. So there is the first thing you want to do. X-axis labeled, Y-axis labeled with the scale. So we get in the Ferris wheel right here at ground 0, right there. As it rotates, 1 full rotation will put us back to 0. Another full rotation will put us back to 0, back to 0, back to 0. That's 4 full rotations. When we are halfway, we'll be at the top. That'd be here. When we are halfway between 1 and 2, 1.5 rotations will be at the top. 2.5 rotations, again, at the top. 3.5 rotations and at the top. Okay, so there's half. So I guess I could mark these as well. And then when I go to a quarter of the way, we will be halfway up. So that would be right here. And 3/4 of the way, we'd be here, which is at the same height as a quarter. So that'd be right here. And this is what we keep doing. So I'm just going to keep doing this. Every quarter now is going to end up at 132 feet. And we could break that down even further to be more accurate, but that's pretty good right there. And the hard part now is to draw a straight. Going through this point here, kind of missed that. Oops. It's really difficult with this pen. But anyhow, you go up, it curves, it comes down. It curves, comes down, back. Okay, I'm off a little bit, but it's tough to do with this. It is tough to do with this pen. Okay, so there it is. That's kind of what it looks like. It kind of would curve and slow turn at the max and then start going back down like so. This should probably, oops, this should be more along this line right here. Okay, and so let's just fix that. Just clean this up a little bit, but you get the idea. And again, this is pretty bad. Kind of more like that. Okay, so anyway, it is just a sketch, but then that should come up and actually touch up at the top and then come down. So there it is. It kind of looks like a sine curve. They call it sinusoidal curve. And that would be the graph of the height of the car. Okay, page 2 says, part B, what type of function would best model this situation? Okay, well, that would be a sinusoidal graph. Okay, a sine graph of the sine function. Exercise 1 through 5. Suppose a Ferris wheel has a diameter of 150 feet. From your viewpoint, the Ferris wheel is rotating counterclockwise. We will refer to a rotation through a full 360 degrees as a turn. A, create a sketch of the height of a car that starts at the bottom of the wheel and continues for 2 turns. Okay, so here we go again. Here is the first thing you do is draw a coordinate plane. Obviously, we're focusing on the first quadrant because we can't have a negative number of rotations and we can't have negative height. The Ferris wheel doesn't go underground. Okay, so this time we are going to do 2 turns and a height of 150 feet max. Okay, suppose the Ferris wheel has a diameter of 150 feet. Let's just assume that the car is right at the ground level. So we're only going to go up to 150 feet. So this is 150. So halfway would be 75. And a quarter would be 37.5. And add 37.5 to 75, and that's 102.5. Is that right? You're going to have 0.5. 7 plus 5 is 12, 7, 8, 9, 10, 112.5 is right here. Okay, so number of rotations is 2. So if I bring this all the way out here, there's 2, there's 1, there's 1.5, there is 1/2 rotation. Okay, so here's how we graph it. We're starting at ground 0. We're going to be at ground 0 after 1 full rotation. We're going to be at ground 0 at 2 full rotations. At 1/2 a rotation, you're at the maximum 150 feet. At 1.5, you're at the maximum of 150 feet. Okay, at the quarter, you are at the halfway point of 75, which is here. And at 3/4, you're at 75. And at 1 1/4, 75. And at 1 3/4, 75. And then you sketch this. So it's going to come up. I'm going to go slower this time so I can make it neater. Come down. Go up. Missed that just a little bit. Come down. And there's the graph. Okay, so explain how the features of your graph relate to the situation. Okay, so then you would just explain what your axis means. So the maximum value is the diameter of the Ferris wheel in feet. The graph repeats because we graphed 2 turns of the wheel. The minimum value occurs when the passenger car is at ground level or 0. Okay, number 2, suppose a Ferris wheel has a diameter of 150 feet. Here we are again, 150 feet. From your viewpoint, the Ferris wheel is rotating counterclockwise. Your friends board the Ferris wheel and the ride continues boarding passengers. Their car is in the 3 o'clock position when the ride begins. Okay. Create a sketch of the height of your friend's car for 2 turns. So what they're saying is you get in the car at ground level and it moves and stops when the next car is at ground level and they're loading. The next group get in and then it moves again, then stops. They're going to keep doing that until you get all the way around and it's full, and then you start to go. So they're saying that the ride's going to start when they are at the 3 o'clock position. So they started filling the car, and when the first car was filled, they would be at the 9 o'clock position when you got in, for them to be at the bottom when you were at 3 o'clock. So then the ride begins, and that's what we're going to graph. Okay, so here is our axis of our X and Y axis, and we are going to, we're going on 3 o'clock position, 150 feet, and I didn't say how much we're going to rotate. The car in create a sketch of the height of your friend's car for 2 turns. Okay, so there it is. So 2 would be all the way out here. 1 would be here. A half would be here. 3/4 is here. Okay, the height is 150 feet. Half of 150 is 75. Half of 75 is 37.5. And halfway between is 112.5. All right. So we are starting the ride at 3 o'clock. Well, 3 o'clock is halfway. So if we have a Ferris wheel, we are starting right here at 3 o'clock. And it's rotating counterclockwise, which matters in this problem, because if it was clockwise, did it say counterclockwise? Yes, counterclockwise. So this is going up and going this way, counterclockwise. So from our starting point of halfway, 75 feet, we're going to begin going up. If it was clockwise this way, our graph would go down first, then go back up. So we are going up. So we're going this way. And when we are up here at 1/4 of a rotation, we would be at the maximum. At a half rotation, we'd be down here again at 75. At 3/4 of a rotation, we're at 0. So we'd be right here. And then at the next quarter, we'd be back up to 75. And then the next quarter, we'd be at the top. And then the next quarter, we'd be at the 75. Next quarter at the bottom. And then we would end up 2 full rotations. We'd end up back there. So this went up first, turned, came down, and did this. Okay, getting better at drawing these. So there it is. There is the graph of that ride. Okay, this is page 3. Part B says to explain how the features of your graph relate to this situation. So what we would say is, the maximum value is the diameter of the Ferris wheel in feet. The graph repeats because we graph 2 turns of the wheel. The minimum values occur when the passenger car is at ground level. The vehicle intercept of the graph, the vertical intercept of the graph is 0,75. In other words, the y-intercept. Because we started graphing when the passenger car was at the 3 o'clock position, which is half the distance to the top of the wheel. Okay. Number 3 says, how would your sketch change if the diameter of the wheel changed? Okay. So you'd say the maximum and minimum heights would change. I don't agree with that. How would your sketch change if the diameter of the wheel changed? The minimum wouldn't change because you wouldn't have the Ferris wheel way up high. You wouldn't be able to get in it. The maximum height would change. The minimum would not. So I'm going to cross that out. So the maximum height would change. The distance between the maximum and the minimum height is the diameter of the wheel. That's true. The sketch would have a vertical stretch or a shrinking of the original sketch, depending on whether or not the diameter was respectively larger or smaller than 150 feet. Okay, we'd still want the minimum at 0. We're not going to go underground because we made the Ferris wheel bigger. We're not going to leave the hub in the center at the same level if we're going to make it bigger, because we'd have to dig in the ground and you'd go underground part of the way. And if it was smaller, then you would need some type of stairs and platform to get up to the level, because it's not at ground level anymore if you made it the same center with a smaller diameter. So number 4, if you translated the sketch of your graph down by the radius of the wheel, what would the x-axis represent in this situation? Okay, you say the x-axis would represent a line through the center of the Ferris wheel that is parallel to the ground. Okay, so we translate it down by the radius, we're moving it down halfway. Number 5 says, how could we create a more precise sketch? Okay, so as I did this, you noticed I plotted the zeros first, the ground level when we were on the ground, when we were at the maximum, and then halfway in between. We could continue doing that to get more precise. So we could measure the height at smaller and smaller increments of rotation. Okay, page 4, exploratory challenge 2, the paper plate model. It says to use a paper plate mounted on a sheet of paper to model a Ferris wheel, where the lower edge of the paper represents the ground. Use a ruler and a protractor to measure the height of a Ferris wheel car above the ground for various amounts of rotation. Suppose that your friends board the Ferris wheel near the end of the boarding period, and the ride begins when their car is in the 3 o'clock position as shown. A, mark the diagram below. So hopefully you understand what they're saying there. When they load a car, when they load a Ferris wheel, you get in here, and then the car rotates to here, and then this car is car number 2. They load that. So if you were in car 1, now when you go to here, now this is 1, this is 2, and 3's on the ground, and they load that. So you keep stopping until you fill up, and that's what they're basically saying here. And it says when the ride begins, you are here. All right. So it says, mark the diagram below to estimate the location of the Ferris wheel's passenger car every 15 degrees. All right. The point on the circle below represents the passenger car in the 3 o'clock position. So the first thing I would do if I were doing this with a paper plate, obviously I can't do it with a paper plate without using video, but I'll do it right here. So this is a paper plate, and this is our piece of paper. But it says this should be ground level. So the ground is actually right here. So I'm going to draw a tangent line right here for starters. This is going to be our ground. Ground level's right there. And then I'm going to move this up like so. And I'm going to draw a diameter. This is the diameter of the circle. Okay. And then I could do a construction with a compass. And if I put my stylus right here and open this up more than halfway, okay, these are constructions from geometry last year. And I drew an arc here and here, and then move this over here like so. I am creating a perpendicular bisector. And what will that do? That will find the center. So if I go like so, and I put this on like this, and draw this, okay, it's off just a hair, but you get the idea. Then get rid of these lines. And there is my paper plate broken into quarters. Okay, so I don't need this anymore. Now I need a protractor. So I take my protractor, and let's shrink it down a little. We want the protractor at the center. We want the crosshairs right at 0, 0, right there. Okay, actually, let me make these lines thinner. Woo! All right, so let's do this. Actually, that is thin. Huh. Can't make that thinner? I guess not. All right. So let's put this back. And we want to let's go to a highlighter. Mark the diagram below to estimate the location of the Ferris wheel passenger car every 15 degrees. Okay, so now I'm going to go back to my pen and let's mark with red, I guess. Doesn't really matter. I want to shrink this way down. Okay, so let me make it larger again. So 15 degrees is halfway between, so that'd be 15, 30, and so on. So I guess one way I could do this so we can all see it is just to go out to here, and I'll put a dot here. So this would be 15 degrees right here. 30 would be right here. 45 is right here. And 60 is up here. 75 here. Actually, it's more over here. 90 we already have. 90 plus 15 is 105. 130 or 120, I mean, 120. 135. 150. 165. And 180 we already have. So let's just do those for starters. So then I bring my ruler over. And as you can see, I can kind of cheat here. My ruler gives me the degree angle. So if I just make it 15, obviously you can't do this in the real world on a piece of paper. So that's why I was showing you with the protractor. And let me just put this at 0 so I can just rotate it. All right, so here's where the car is at 15 degrees. Move this to 30. And the car is here. Move it to 45. Okay, like so. And I'm gonna just do this behind the scenes because I think you get the idea. Okay, so there is my Ferris wheel with every 15-degree rotation. So there are all the cars. So how many cars is that? There's 1, 2, 3, 4, 5, 6 times 4 is 24. Okay, 15 times 24 should be 360. Okay, so then it says, since this is the beginning of the ride, consider the position to be the result of rotating 0 degrees at the 3 o'clock position. So we started here, 15 degrees, 1, 2, 3, 4, 5, all the way around 24 times. So now B says, using the physical model you created with your group, record your measurements in the table, and then graph the ordered pairs rotation height on the coordinate grid shown below. Provide appropriate labels on the axes. Okay. So rotating 0 degrees, we started here. What's our height? What is the height of this thing anyway? Does it say? Use a paper plate mounted on a sheet of paper modeling the Ferris wheel where the lower edge of the paper represents the ground. Use a ruler and protractor to measure the height of the Ferris wheel. Oh, ruler and protractor to measure the height of the Ferris wheel car above the ground for various amounts of rotation. So I want to measure the height of the Ferris wheel from ground up. So this is the ground right here. And it looks like 5 centimeters. Okay, so this appears to be right about 5. There's 0 right there. Actually, it's more. It might be different on your plate, obviously, but I have 5.2 centimeters, 52 millimeters. And that is after a 45-degree rotation. We're at the maximum height. So after 45 degrees, we are at 5.2 centimeters. Okay. Okay, so obviously your paper plate's gonna be way bigger than 5.2 centimeters, but I'm just doing this in a diagram to show you how to do it. So the first thing I would do is say, okay, well, rotating 0 degrees, we're at the maximum. And I'm gonna do the easier part. So half of 52 is 2.6. So at 45 degrees, which is here, using the physical model you created with your group, record your measurements in the table and then graph the ordered pairs rotation height on the coordinate grid shown, provide appropriate labels. Where are we starting? The beginning of the ride, consider the position to be the result of rotating by 0 degrees. So this is our 0 degree rotation. We are not at 5.2, which is up here. We are at 2.6. Half of 5.2 centimeters is 2.6 centimeters. So this is 2.6. Okay, so I'm going to move this down to a 45 degree rotation. We're at the maximum. So this is going to be 2.6. And I'm going to do the easy ones first. So a 90 degree rotation, 15, 30, 45, this actually is 90. A 90 degree rotation will get us to the maximum. Okay, and then we continue rotating. This is a 180 degree rotation. We are at 2.6 again. And then another 45 degrees, we are at 270. We're at 0. And then another 45 degrees, 360 degree rotation will put us back to 2.6. So 2.6, where's our other? We went from 2.6 to 5.2, back to 2.6, down to 0, 2.6, and repeat. So at 15 degrees, now I need to measure each one here as accurately as possible. So this is 0. So if I go up to this point right here, it looks like about 3.2 centimeters. And that's a 15 degree rotation. Okay, so that's 3.2. Well, where else is that going to happen? At a 180 minus 15, which is 165, we're going to have a 3.2 rotation. Okay, so do 2 at a time. Then I'm going to measure the next one. Can I just tap that over like this? Nope. All right. So let's just move this over to here. Get as close to 0 as possible. This is 3.567. That looks like 3.8, I will say, 3.8. And that is a 30 degree rotation. So that would be that'd be over here, which is 30 degrees less than 180 or 150. So I'm working this way. So we're coming together towards the top. Put one here, 45, 135, 60, 120, 75, 105, 90, and 90 is equal. Okay, so there's one more. Move this over to here. And that looks like 4.4. So I put 4.4 to 45 and 4.4 at 135, which would be right here. Bring this over. This looks like 4.567 or 4.8. I'll say 4.8. This would be also 4.8. And then the last one up here is looks like 5.1. I'll say 5.0. Okay. Now, obviously, the distance from 2.6 to the next one would be the same as the distance 2.6 to this one, but I'm going to measure them anyway, rather than doing the calculation. So when I measure this, I'm at, it looks like 2. And that does come out because this was a distance of 6, 6, 6. That's only 4 for some reason. 2. So I don't know. Anyway, not perfect. So at 195, which is right here, is the same as 45 minus 15, or 360 minus 15, which is 345, which is here. I just measured the 345 rotation right here, and it's showing to be, it looks like 2 or 2.1. I will call it 2. So this is also 2. Now we're working towards the 0. Now we're moving down. So if I move this over now, this looks like 1.4. I'd go here and here. Move this over. And that looks like 0.8, 0.8, 0.8. Okay, and then we're moving closer. And that looks like approximately 0.4 and 0.4. And our last measurement finally, and that looks like 0.2. Again, it's not perfectly accurate, but you get the idea. These all should be the same distance. And I have a distance of 4 here and a distance of 6 here. So something's off a little bit. Okay, but that's the idea. Okay, page 5, now we're going to graph that. So what I've done is brought in my table down here that I created on the previous page so I don't have to go back and forth and so on. So we're going to now plot these points. All right, so rotation in degrees should be your x-axis. So this is rotation in degrees. Okay, and your other one is your height in centimeters. Okay, so always label your x and y axes. Okay, and I'll even put that there. All right. So now we're going to plot 0. We were at 2.6, which is about here. At 15 degrees, we were at 3 and a little more. At 30 degrees, we were at 3.8, which is even higher. At 45 degrees, we were at 4.4. So this is 5, so it'd be about here. Okay, so as you can see, that's a nice curve coming up slowly. 60 degrees is 4.8. So here's 4.8 right about there, not quite 5. 75 degrees, we were at 5. At 90 degrees, we're at 5.2. Actually, that's an 8. Let me do this again. I don't like the table they used because why are we going so high, 36? Let me think about this a second. Okay, they're obviously doing the plate here. So I would change these values for my table, but they gave us these 36s. My maximum height was 5.2 at 90 degrees. So I would I would actually change this to, let's see, we have 1, 2, 3, 4, 5, 6. Let me just do that. I'll go by ones. So I'm going to get rid of this scale, and this is going to be 1, and this will be 2 centimeters, and this is 3, and this is 4, 5, 6. That's as far up as I'm going to go. So let's start this over. 0 is 2.5 is here, so 2.6 would be here. 15 is 3.2. Okay, here's 3.5, 3.2 would be about there. 30 is 3.8. Here's 3.5, 3.8 is about there. 45 degrees is 4 and not quite a half, 4.4. 60 is 4.8, which is about there. 75 is 5, right there. 90 is 5.2, which is a little bit higher. And 105, which is here, is back down to 5. So as you can see, we hit our maximum. We're curving up, and now it's turning. And then it's going to be 120 is going to be 4.8, which is about here. And 135 is 4.4, which is about here. And now I'm just copying these distances. See this one here, and then I'm just going to come over just to save time. And this one here is going to be here. Okay, so that is, now we're at 9 o'clock, 180-degree rotation, and now we're going to go down towards the ground. So now we're at 195, which is an even 2.0, which is here. 210 is 1.4, which is below 1.5. 225 is 0.8, just a little below 1. 240 is 0.04, below 0.5. 255 is 0.2. And 270, we hit 0. And now we're just going to copy this value over. Copy this value over. Copy this value over. Keep doing that. It gets quick once you get half done. And there we are at 360 degrees. So there is our curve graphed. That turned out pretty nice. That is a sinusoidal curve with a maximum of 5.2 and a minimum of 0. So the midpoint of that, which is our 45 degrees and our 180-degree rotation, came out to be 4.4. Or it's actually 0, 2.6, 2.6, 0 and 360, and 180, 2.6. Okay, so there it is. Closing. How does a function like the one that represents the height of a passenger car on a Ferris wheel differ from other types of functions you have studied, such as linear, polynomial, and exponential functions? So you'd say the domain values represent the rotation measured in degrees of a car on the Ferris wheel from the 3 o'clock position for one turn of a passenger car. The range values represent the height of the car above the ground, which we modeled using the bottom edge of the paper. The vertical distance between the maximum and minimum values is the diameter of the paper plate measured in centimeters. Okay, so obviously your paper plate would be bigger than 5 centimeters. So there we have it. Okay, page 6. What is the domain of your Ferris wheel height function? Okay, so domain is your X. So if I think about that, well, it's a full rotation. So it's from 0 degrees to 360 degrees. Okay, so the domain is 0 to 360. The range, in my situation, the range was the ground, 0, and the maximum height, which I think was 5.2 cm. So actually, I should probably do this. 0 cm to 5.2 cm is the range. Okay, provide a definition of periodic function in your own words. Why is the Ferris wheel height function an example of a periodic function? Okay, so it would be a periodic function is a function returning to the same value at regular intervals. Okay, so here's just a couple of examples. The movement of the planets around the sun. Okay, another one would be the motion of a yo-yo. If you know what a yo-yo is, yo-yo goes down and up and down and up and keeps repeating. Okay, so there's 2 examples. Okay, page 7 brings us to the end of lesson 1 from module 2. Go to your problem set.